Thus far, I have assumed positive numbers only, and all the arithmetic circuits we built, like the adder and the adder subtractor, were built considering positive numbers only. So it did not consider any negative numbers, and it also assumed that the results are always positive. However, this might not be always the case, and in this video, I just want to show you how we deal with signed numbers, and I'll also take the adder subtractor circuit and modify it a little bit to give me a flag to indicate an overflow, which is just a flag that tells me that the results are wrong and you shouldn't trust them. So let's get started. So I will start by talking a little bit about how we represent signed numbers in binary. So as it turns out that there are three different ways, at least three different ways to represent negative numbers in binary. There's a signed and magnitude, and there's a ones complement in here, and there's a twos complement in here. You might be already familiar with them, but I'll review them just to show you. So in this discussion, I'll explain the differences between the different representation using a sequence of ones and zeros. So in here, I have the least significant bit is 0, followed by 1, followed by 1, followed by 1. And it's the same sequence of ones and zeros. And we'll see shortly that the different representation, actually you can see them here, the different representation represent them or interpret them completely differently. They're the same sequence of zeros and 1. But before I get started talking about it, I just want to mention that I am assuming that my numbers in here are 4 bits. Okay, so I mean the same applies to something a little bit, or numbers that are a little bit larger. So let's talk about it. So how does the sign and magnitude actually work? Well, the sign and magnitude, and frankly speaking, all representation, you take a look at the most significant bit. If it's a 1, generally speaking, it's a negative number. So I'm going to assume, okay, this represents the sign. So in here, I'm telling you that's a sign number, and then the sign and magnitude is pretty straightforward. The way you do it is you tell me, okay, this is the sign and it's a negative, and the number next to it in here is actually the magnitude. And if you know your binary, you would know that this is a 6, and this is what you see in here. This tells me that this is a -6 in decimal. Okay. How about the ones complement? Well, the ones complement, again, you take a look at the most significant bit, it's negative number. So, and you know it's a negative number. That means in order for you to know what number it is, all you have to do is take its ones complement. And as you probably know, ones complement is just you complement it every bit separately. So that will be the number 1, 0, 0, 0. And that is exactly what we have in here, which is -1. Okay, so that's a -1 in decimal. And lastly is actually the twos complement. And in the twos complement, again, I'm going to take a look at the most significant bit. It's a 1. That means that's a negative number. I need to take its twos complement to figure out what that number is. So I'll take a 0, a 1, and then followed by 0, 0. And that is exactly what we have in here, which is a -2 in decimal. So again, as you see in here, is like the same sequences of ones and zeros. A different representation will interpret them completely differently. And this is a pattern actually in digital circuits and actually in computers in general. A sequence of ones and zeros can be interpreted differently depending on what you want to do with them. So we have adopted twos complement throughout this module, and frankly speaking, in most of digital logic and most of computing, we implement twos complement because of the simplicity of doing subtraction. And we're going to continue this. So in the next discussion, you will see that I'm going to only adopt twos complement. However, there are ways to implement signed magnitude and ones complement in circuit, but they're just a little bit more complicated, so we're just going to avoid them, because the twos complement just does the job. Okay, so let's see a few arithmetic involving negative numbers. So in here, I'm showing you a few examples. I'm going to walk you through all of them, and I'm going to show you how we can do them. And in all the numbers, I just want to make sure that you see it in here. All the numbers, I'm going to consider them as 4 bits, as I did a few seconds ago. And because it's a 4-bit, we know if it's 4-bit, that means you have 1 for the sign and 1, 2, 3 for the magnitude in here. Well, it's not a sign magnitude. Even in twos complement, you know that you only use 3 numbers, well, more or less 3 numbers for the magnitude. Anyway, what I'm trying to say in here is if you have 4 bits, that means you have a number from -2 to the n-1. In this case, n is 4 minus 1, which is -2 to the power 3, and that's where the -8 came from. And you go all the way from 2 to the power n, and this is basically -1, okay, or n-1 here. Okay, 2 to the power 4, or 2 to the power 3 minus 1, that's 8 minus 1, which is 7, and that's a +7, and that's where this number came from. Great. Okay, so that's fine. So now we know that the numbers or the results, if I'm using 4 bits, should fit in the range between -8 and 7. If I get anything outside that range, I'll get an error. So let's get started. So in here, I'm going to start with this one in here, and I'm taking a look at it. Well, what I have is I have a couple of positive numbers, +6 and +3. If I add them, I should get +9. So let's see what happens in binary. And this is a 6 and this is a 3. And of course, the most significant bits are 0, indicating it's positive. And I'm just adding them. All you have to do is just add. So I'm going to add them in binary. And that's 0 and 1 is a 1. And then 1 and 1 is 0. And the carry is 1. And let me just do this as a carry is 0. And then 1 and 1 is also 0. And the carry is 1. And then this is 1. And of course, the carry out is 0. I don't have to say it, but the carry out is 0 in here. All right, so let's take a look at that. So the number in here tells me, well, wait a second. The number tells me that it is, you might see it as a 9. However, I want you to emphasize the following. I'm dealing with signed numbers now. So any patterns of 1s and 0s should be interpreted as a signed number. Taking a look at the most significant bit, that's a 1. That means this number should be negative. So technically, if I'm dealing with 2's complement, this number is 1110. This is actually a -7. That's what I got. Okay, so what I did is I added a 6 to a 3 and I got the number -7. Huh? Why did I do this? Well, the answer is because a 9 is outside that range in here. It doesn't fit in 4-bit if I'm dealing with it as a signed number. This concept is really important to understand. So what I want you to see in here is the following. If you're adding two binary numbers, you will get, technically you will get the correct answer. However, if you're interpreting these binary numbers to be signed numbers, you're going to have to be careful about your results. So if your result, for example, in here, I added a positive number, I added a positive number, and I got a negative number. So there is definitely something wrong in here. Let's continue. I'll just see where can I get like negative, like wrong answers or whatnot. So we'll see in here. So in here, I'm going to do a -6 plus 3. And because this is a -6, I will represent it in 2's complement. I already done that for you. I just took the 2's complement of this guy and I just placed it in here. And now I can just add them up. So the way we add them is this is a 1, this is 0, 1, okay. And this is, hold on, 0, 1. Let me just clear it up a little bit here. And here, okay, just write it clearly. 1, and the carry out is 0. And then I have a 0, and then 1, and then there's a 1 in here, and there's a 1 in here, and of course the carry out is 0. And if you take a look at this, this is a negative number, so in order for me to know what it is, I need to take its 2's complement, and that's 1, 1, 0, 0. So that's technically a negative, whatever that number is, which is -3. That's exactly what I expect. -3 plus 3 is -3. So that's good. Again, I'm interpreting these as signed numbers. This is why I'm considering this to be -6. However, if you actually think about it, and if you're dealing with it as an unsigned number, this will not be a -6. This will be a 10, okay, and a 3, and you should be getting a 13, and that will be a 13 if you're interpreting them as unsigned. But anyway, we're dealing with these as signed numbers. So we go in here, and now what I have is a +6, -3, and of course the answer should be 3. And that +6 is the same as that one in here, and the -3 in here, which is just the 2's complement of this guy, which is pretty much the same answer we got in here anyway. So if you add them up, you're going to get a 1 and a 1, and then a 0, 1, and then a 0, 1. Okay, and how many bits we have? Well, I have 4 bits, so I can technically ignore that carry out that what I got in here. Okay, I'm going to consider this as a carry out. And the answer is +3 as I expected. So as it turns out that the carry out, if you deal with signed numbers, the carry out is meaningless. You don't need the carry out because sometimes it's 1, but it's really not a 1. Okay? Because what you care about is the most significant bit here is 0, and the carry out you just ignore. Okay? So let's finish this, and I'm going to take a look at the last one. The last one, I just basically took a -6 and a -3. Of course, -6 from here and -3 from here. They're the 2's complements of the 6 and the 3. And if I add them up, I should get a -9. I should get a -9, but as we probably know by now, that will not fit within 4-bit. So I'll get probably a wrong answer. So let's see this. This will be a 1, and a carry here is 0. This will be a 1, and a carry here is 0, and this will be a 1. And the carry here is 0, and that will be 0, and then there's a 1. And of course, that's a carry out. So technically, I should just not consider the carry out, or I should just ignore it. And then I'm going to take a look at this. And there's obviously something wrong. This is the number 7. This is not a number -9. Okay, and of course the number is wrong. Okay, so let me just recap what I've done in here. What I've done in here is I showed you a couple of things. If you're dealing with signed numbers, like in this case, that means to carry out, whatever carry out you have here, here, or here, or here are meaningless, and you shouldn't be even looking at them. They're completely meaningless. Okay? And if you're dealing with signed numbers, you might get a number that does not fit within the number of bits you have, and you're going to get an overflow. And that was this case in here and this case in here. Okay? So the overflow, and why am I talking about overflow and carry out, is because all I'm doing in here is, my ultimate goal is I want to modify the adder subtractor circuit that we developed so that it gives me an overflow indicator. That I want it to give me a 1-bit indicator that tells me, well, the answer here is wrong and the answer here is wrong, but the answer here is right and the answer here is right if you're dealing with signed numbers. Okay? So how do we go about this? So let's go to Vivado and just figure out what we need to do there. So I went ahead and I created a new module, and now I called it an adder subtractor. Okay, and the last one we developed was an adder subtractor n-bit, and I just removed the n-bit, and it will be an n-bit, but this will be the final adder subtractor we developed because this is the complete one that should have everything. And frankly speaking, what I went and I copied the code from the adder subtractor n-bit, and I just put it in here. So there's no difference between them whatsoever. And just as a quick reminder, what it has a ripple carry adder, and it has the bunch of XORs in front of it, and it has the add subtracts input, or the add in. Okay. All right. So what do I need to do? Well, really, my ultimate goal is this is an adder subtractor. I want to utilize it with signed numbers. So all I need to do is to add an indicator to tell me whether the answer is right or wrong if I'm dealing with signed numbers. So X and Y, if you're interpreting them as unsigned numbers, everything works the same. But now if I want to interpret them as signed numbers, all I have to do is just say, well, my output here, I'm going to say something like an overflow. So I'm going to create another signal here. It's another output, and that output would be just an overflow. Okay. So if the overflow is on or it's high, it tells me that the results are wrong. So how do I go about this? I need to modify this code somehow. Again, this is something that sometimes I do myself. Like I want to do something, and what I do is I go ahead and I jump to the code and I try to modify the code. You shouldn't. You should take a look at your design before you actually jump and modify the code, at least most of the time. Okay, so how do I create an overflow? Well, I frankly speaking don't know, but I'm going to take a look at these examples that I have in here, and I'm going to figure out what I should do. So what I have in here is I have a couple of examples, and let me just highlight them here. This example should give me an overflow, and this example should give me an overflow. So let's take a closer look at it. So, and as it turns out, I mean, you don't have to know it or see it. It's not as clear as I would like it to be. As it turns out, if you take a look at the very last bit, or the most significant bit in the full adder series, okay, you will have a carry in and you'll have a carry out coming out of it. And of course, you will have the sum in here, but I don't care about that. What I really care about is this guy little here. Actually, the carry in and the carry out. And as it turns out, if they're different in the most significant bit, if the carry in for that full adder is different than the carry out, you have an overflow. Well, let's see this in here. So we have this guy in here and this guy in here. They're different. So there's an overflow. And well, let's take a look at these guys in here where there isn't an overflow. There's a 1 in here and there's a 1 in here. So there isn't an overflow. And here, I bet you it should have been 0. I probably forgot to write it, but this should be a 0 and this should be a 0, and there's no overflow. So it could be as easy as you go back to Verilog and you go to the last full adder, you just check it's technically it's carry in and the carry out, and you take the XOR between them. If XOR tells me it's exclusive OR, it's basically the asymmetry gate. And if it's a 1, you have an overflow. However, this is not very intuitive, and I do remember it. For some reason or another, I do remember it, but sometimes like I forget about adder subtractors and I forget about it. So there's an easier way to do that. It might cost us a little bit more gates, but it's easier. So let me explain. So as it turns out, if you're actually having two numbers that are -6 and a 3, or two numbers and one is a positive, the other is negative, they don't share the same sign, technically you're subtracting them. So if you're subtracting them and they're correct, they fit within the 4-bit, the answer will be within the range. I mean, you're not exceeding the range. There's no way, if you're taking away from a valid range, like some number that is also valid, it will give you a valid answer. So in short, these two in here, I have one positive and one negative, so the answer is correct. So what I can do is I can assume that that's always going to be okay. We're not going to have an overflow in here. However, we're going to have an overflow in the following case. If I have the following, the sign of the inputs are both positive, but the sign of the output is a negative. Well, something wrong has happened. I'm adding two positive numbers. How can I get a negative number? The same goes in here. I'm adding two negative numbers. I should not be getting a positive number. So you can detect an overflow by taking a look at the most significant bit of my inputs x and y, and my output, the most significant bit of my output is sum. And that's what we're going to do right now in Verilog one more time. Okay, so now I have my overflow signal. All I have to do is just assign some numbers to it. And again, I'm just going to do the following. You can insert this statement anywhere. So I'm going to say assign overflow, and what I will do is I will say, okay, what inputs do I have in here? I have an x and I have a y, and the most significant bit is n minus 1. So I'm going to say okay. So let me just say x of n, okay, or n minus 1, sorry, okay, because I mean 0 to n minus 1, and I'm going to do x ORed of y of n minus 1. And the reason why I'm doing the XORed will be obvious in a second, okay? And I will do that now. These two share the same sign. If they're both positive, that means the sum of n minus 1 should be negative. So what I'm going to do is I'm going to say not in here, okay? And that's, I'm saying the x should be, the most significant bit of the x is positive, the most significant bit of the y is positive, and the most significant bit of the sum is negative. That means something has happened and I got an overflow. But this isn't the only case. The other case is actually when the most significant bit of x and the most significant bit of y are both low or 0, and it just happened to be that the sum of n minus 1 is also high, or high, which is opposite to the other. So that means I'm summing a couple of negative numbers and I got the sum to be 0. Of course, this one, I changed it to XOR, so let me explain why did I change it to the XORed version of y. So I could have done y, and that would be completely fine. However, all of these examples that you see in here, if you paid attention, I never actually done any negative. It's always positive. So I only showed you the adder version of the adder subtractor. However, the subtraction is pretty straightforward. I mean, you can expand the same ideas exactly. And for example, let's assume that you want to do a negative in here. All you have to do is just take that negative, put it in here, and you have 6 minus 3. Okay, so what I did in here is I just placed the overflow on the entrance of the adder. Okay, on the entrance of the adder, because this is what I care about, because I only care about the adder, not the adder subtractor. Okay, so I took the x, and if you remember, the XORed is actually the negated, well, it could be the the one's complement of y, or because we add 1 to the carry in. Anyway, so I'm doing it this way. That means I only care about detecting the overflow from the adder, because anyway, I'm doing subtraction using addition. Now my circuit is complete, so I just want to test it. So I have a really good adder subtractor. Let's take a look at the inputs and output. I have a complete adder subtractor. It takes a couple of inputs of any size I want. By default, it's going to be 4, and it can take a signal that can add or subtract based on, like, if it's a 0, it adds, if it's a 1, it subtracts, and it gives me a sum, and it gives me a carry out and an overflow. So what I want to do right now is I just want to go and test it, and I will just test it on the board. So I'm going to have to go and create and generate bitstream and so forth, and I'll do this and come back to you guys. Of course, before I do that, I need to actually create a constraint file. I've already done this. So in the constraint file, let me just show you what's in that constraint file. In the constraint file, I'll just add the adder subtractor in here so that you get to see it. So in the constraint file, I need some inputs and outputs. I'll have to make this as my top file. Okay, so I'm going to go in here and I'm going to say my adder subtractor, not the n bit, but this one will be my top file. Okay, this is the file I want to test. Since I'm not instantiating this anywhere, I'm just using it as my top file. It will take the default value of n, which is 4-bit. Okay, so that's fine. And now let's see what I need. I need 4 input for X and 4 inputs for Y, and that's exactly what I did with the switches. So I have went from X0 all the way to X3, and I have from Y0 to Y3, and these are the first 8 switches I have. And then of course I need a signal to whether to add or subtract, and just so that it's not very close to the numbers, I put it the most significant switch, which is switch number 15 in here. And then I wanted to show the results, and the results I'm going to show them on the LEDs. I took that S in here and I just put them in the 4 least significant bits of the LEDs. These are the LEDs on the very right. And then I'm showing these 2 flags, which is the carry out and the overflow on the very other side, or on the very left side of the LEDs, the last 2 LEDs. And all I have to do after I made it my top file and I generated my XDC file, all I have to do is just click generate bitstream, and it will create that bitstream for me, and I'll have to upload it to the FPGA and just test it. So let me show you. So I went ahead and I uploaded the program to the FPGA board, and as a reminder, I have the 4 least significant switches representing the X, and the next 4 significant switches are actually the Y, and I have the one here, which is switch number 15, represent the add subtract. If it's a 0, it's a add. If you set it all the way up, it actually is subtract. And of course I have a few LEDs in here. The first 4 LEDs will tell me the sum or the subtraction result, and then the last 2 LEDs in here, the very last one will show me the overflow, and the one before it will show me a carry out. So let's go ahead and test it. The circuit is an adder subtractor. First, you're going to have to figure out whether I'm actually dealing with signed or unsigned numbers. So I'm going to start by explaining it with unsigned numbers, and I'm putting this here because I kept messing up when I was recording. I kept saying signed and unsigned, and now I know I'm dealing with unsigned numbers. So unsigned numbers, there's no negatives. So for example, let's say that I want to add a 6. So my X would be a 6. That's a 0, 1, 1, and that's a 6. And of course 6 plus 0, because the Y is still at 0, is a 6, and that answer is correct. So that's the first test. And then I'm going to go to this Y, and I'm going to say, well, I'm going to say it 1 and 1, and then 0, 0, and then I'm going to take a look at the number. So I'm adding a 6 to a 3, and I should expect a 9, and that's exactly what I got. But one of the lights got lit in here, but that's the overflow. Frankly speaking, because I'm dealing with unsigned, I don't care about it. So whether it's on or off, it doesn't matter for me, and I can test it accordingly. Okay, that's perfect. So now that's the addition. Let's test the subtraction of unsigned numbers. Okay, so I'm going to do this in here, and then now I'm subtracting 6 minus 3, and I'm getting the number 3. And now the other light got lit, and that light is the carry out. However, it's a subtraction. In a subtraction, the carry out is actually meaningless, and we don't use it. So that's perfect in terms of an unsigned number. Now let's do the same exact thing. The switches are almost exactly the same. The numbers are still a 6 and a 3. Okay, and now I'm doing addition. In the unsigned, it was the answer is 9, and I had an overflow. But now what I'm going to do is I'm going to say, okay, let's consider them as signed. Okay. Here. So I'm writing now signed. So these numbers now are signed. Okay, because they're signed, now I can think about it. I'm adding a 6 and a 3, and I should get a 9, but a 9 does not fit in 4 bits. So I'm going to have an overflow, and that's what I'm getting in here. That number in here is telling me that the answer you have is wrong. An overflow has happened. If you're interpreting these as signed, this number is not a 9 anymore. This number, you're going to have to take the 2's complement of it, because the most significant bit is a 1. Okay, so the 2's complement of this guy is a 1, 1, 1, 0, and that's a -7. And of course, 6 plus 3 should not be a -7, because I'm adding 2 positive numbers. So an overflow has happened. Great. So now, again, it's like if you add the subtraction in here. So the subtraction is telling me the overflow is not lit. That means the subtraction result is correct, even in the signed case. And 6 minus 3 is a 3. In signed, it is correct, and it fits. The carry out in a subtraction operation is meaningless. Okay, so let's test it with a completely different number. So I'm going to just make everything back in here. And I'm going to say, okay, let's add, for example, a 10. Okay, and of course, if I'm saying 10, that means I am dealing with, I can't say signed, because now that number is not a 10 anymore. Okay, that number is completely different. Okay, so now I'm dealing with unsigned, because I can't fit a 10 in a signed number. So that's a 10, and let's assume that I want it to fit 15, or I want to add it to 15, okay? What I'm trying to show you in here is the following. So I can add it to 15. A 10 plus 15 is technically 25. If I'm dealing with unsigned numbers and I'm adding, I can take a look at the carry out, and the carry out is meaningful. And if you think about it, a 10 plus 15 is a 25. What the number I got in here is actually 9, okay, and a carry out. And remember, the carry out in a 4-bit adder equals to 16. So 16 plus 9 is actually 25, and the result is correct. Okay, now let's assume that I want to deal with this particular operation as sign. Now, if I'm dealing with this operation as sign, that means the first x cannot be interpreted as a 10 anymore. I'll have to take its 2's complement. So the 0, 1, 0, 1, well, I'll have to take its 2's complement. That's a 0, 1, 1, 0. Okay, so what's a 0, 1, 1, 0? It's actually a negative 6. So that's a negative 6, and a bunch of ones is just a negative 1. So a negative 6 plus negative 1 is a negative 7. And the overflow is not lit. That means the answer is correct. Is this a negative 7? And the answer is, well, I'm going to have to take the 2's complement because the most significant bit is 1 here. So I'll take a 1, 1, 0. And that's a negative 7. And the answer is correct. And since we're dealing with signed numbers at that point, or with signed numbers, the carry out is meaningless at this point, because the carry out relates to signs, which we can't carry out the sign. And that's how we test it. And you can test it with different numbers just to see it. But the bottom line is, I want you to understand what the overflow and the carry out. The carry out is only meaningful when we're dealing with unsigned numbers and you're just adding, okay? So when you got stuck, okay, so I want to show you that we deal with the carry out if we're dealing with unsigned numbers and you're adding. If you're subtracting, that's it. The carry out is meaningless. Now the overflow, you're gonna have to deal with it whenever you deal with signed numbers, and it tells you whether the result is wrong or not. The carry out is also meaningless in the signed case.